see how this goes. Okay, so just an introduction, just to put you in the picture on robotics and build things up. We're talking about a timeline here. We start around about 1950. And there was a British psychologist called Gray Walter. And Gray Walter didn't know anything about robotics, but he wanted to understand insects and behaviour of animals. So he built these robot animals, robot tortoises, and I'll talk about those a bit later on. Then going on, I've just taken the blue area at the top because Braitenberg released a book called Vehicles, and I'll talk about those. This was one particular route of robotics where people are trying to make machines that will work on reaction. So they will move around, a bit like the robot vacuum cleaner, move around and react to dust in the environment or to the walls, but at least they're constantly moving. So we've got Gray Walter's Tortoise, Braitenberg Vehicles, which leads to behaviour-based robotics around about the turn of the millennium. On the other route we've got, on the red route, we have the artificial intelligence route, which started off with a Dartmouth conference over in America, where the term artificial intelligence was coined. And this approach is looking at robots that plan what they're going to do. So rather than just react to the environment, they think about the environment and they decide which way to go. So you've got the AI planning and a robot called Shaky, which was from Stanford Research Institute, and a whole lot of other robotics here. What we're starting to find is that this approach to robotics, the artificial intelligence, which makes robots move very slowly but very thoughtfully, and the behaviour-based robotics, which makes robots move very quickly but not very intelligently, are slowly starting to come together to make robots which are intelligent but react to things as well. And that's pretty much where we are. But there's two schools of thought here, so I'll talk more about those in a bit more detail. So Walter Gray, he was, I think he was based at Bristol, and you can still see his tortoise now in the National Science Museum in London, and they've got a copy at the Bristol University. So he made a very simple robot. The robot just had a few valves in it, and on top of the robot there was a light sensor. That light sensor spun around with a drive wheel and a steering wheel. So every time the steering was turning, it would turn the light sensor as well. He also put a light source on the robot and a bumper, so it could do something if it hit something. And the back wheels were just passive casters. So there was a simple electronic, there wasn't really a program, there was no way of programming these things, but it followed a simple circuit. So the steering motor turns continuously. If the light sensor detects a moderate amount of light, it would stop turning. So if I put this in the room, the steering motor would rotate, so it would move the robot in a kind of spiral fashion, and it might just detect the light coming from outside. And that would stop the steering motor turning, but the drive motor would keep turning, so it would drift towards the light of the room. And that's moderate light. When it got very close to the window, very bright light would make the steering motor turn twice as fast. So it would get towards the light and then quickly move away again. So you've got this kind of oscillation approach. So that's exactly what would happen. Now, a nice experiment that happened was that Gray Walter created a charging station, a hutch. And for the robot to be able to find the hutch, the only sensor is a light sensor and the bumpers. But the light was on in the hutch. And what happened is the robot would head towards the hutch, but if it's had a nice charge in its batteries, it would then perceive the light as being very bright, so it would move away from the hutch again. But what he discovered was that when the batteries were low in the robot, it wasn't as sensitive anymore. So it would head towards the hutch, but then because the batteries were quite low, it wouldn't perceive that light as being very bright, just because of the amplification circuits weren't running as efficiently. So it would go into the hutch and start to charge up. And when it charged up, when the battery had a certain amount of charge, those sensing circuits became sensitive again, so it would then move its way out of the hutch. So that's a behaviour that just happened almost by chance, that the robot would go into the hutch when the batteries were low, and exit the hutch when the batteries were charged. Wonderful. It wasn't even programmed, and that was something that happened. So this is a kind of a natural behaviour that just emerged from this, and it kind of evolved in a way, because that's what the robot needed, and that's what happened. So it led you to think, well, how does evolution work? You know, it's quite a nice way that things have progressed. The bumper inhibits the light sensor for a certain amount of time, and it enables full power oscillations to the motors, both the drive motor and the steering motor, to try and move an obstacle. So if it hits something, a table, it would try and bash it out of the way. He changed things slightly. For example, he changed it so the light bulb, which is on the back of the robot, there's a picture of the real robot by the way, came on when the steering motors were on. And he started to create several of these, about 5 or 6, put these into a room. So their lights on the back of them would be on and off when the robot was turning. So the other tortoises could learn what was happening, because if the steering motor of another one is on, then their light is on. So it knows that it's either avoiding an obstacle or getting away from a very bright light. And we found that there were certain interactions with these robots. They would follow each other at a certain distance but not get too close. They would flock together. So they had quite interesting behaviours that emerged as a community of robots. Interesting, when they found a mirror, they'd oscillate, they'd be interested and then move away from the mirror. It's interesting though that we put these words to these, you know, I say interested, well it wasn't interested, we know how the thing works, don't we? It was just following that program. But from an external observer who might not know that it's a mechanical creature, they might say, well, it's alive, it's interested in itself, and then it's moving away. So it leads you to think, well, you know, how much can you apply that to life? How much can you apply that to machines? If we judge things from the cover, but from the behaviour, it seems to be very alive. So simple creatures can have complex behaviours, and the complex behaviour is a result of their environment. So if you just put that into a completely empty room with no walls, it wouldn't have a complex behaviour. But with other machines in there, with windows and mirrors, they start to have a complex behaviour. So that's quite an interesting cognitive thought going on. So let's look at the other area that was happening. So over in America, there was a Dartmouth conference, and the Dartmouth conference was run by a lot of computer programmers who knew that they could do something really amazing with these new computers that had just been invented, you know, mostly due to the Second World War. What can we do with these things? So they decided that they could make machines intelligent and have robots to do all our dirty work, basically. So Shaky was developed at Stanford Research Institute, and this took a completely different approach. It was a single robot because it was really expensive. It's full of kit, so it's not small. It doesn't move very quickly, and it shakes when it does move, hence the name Shaky. And it lived in a special room of coloured blocks and wedges. And the idea was to give the robot certain tasks. For example, climb on top of the blue block. Now in these days they're all black and white pictures, so you can't see the blue block. But the robot had to work out, how am I going to get on top of the blue block? There's a yellow ramp. If I push the yellow ramp to the blue block, I might be able to drive up that ramp and get onto the blue block. So that was the kind of things that they were trying to get Shaky to do. Most of the processing was done off-board, so that's why it had transmitters on it, because in those days we didn't have the processing power to put onto a robot. It was all done in a computer the size of a room, so it was all radio linked. Now most of the time Shaky stood still, so if you went into that room you would see something that is just standing still, and then every 5 minutes or so it might leap forward about 10 centimetres, then take another image. So every time it moved it had to take another image, because shadows change, viewpoints change with image processing, and the image has to be reprocessed again. So although it was intelligent in some ways, it could do the tasks, it wasn't intelligent in other ways. You could run up to it and kick it over and it wouldn't know. So, completely different from the other approach of the tortoises, where if you went up to those and kicked them, bumpers that would react straight away. So things are moving on a bit now, still using the idea of image processing and trying to combine it with behaviour. The lab at Stanford Research, Stanford AI Lab, wanted to build a robot to land on the moon. So what was built was basically it was a table with 4 bicycle wheels and a chain. And in 1967, it took someone a PhD thesis to program the robot just to follow a white line. So in 1970, we've got something which is just following a white line, which is a very simple task for us to do now. 1980, it moved up to understanding some of the objects around it, and the idea was, let's get this robot to work outside as part of this moon plan. Now, what happened was, this robot lurched forwards every 15 minutes. It took 15 minutes to process the images. Unfortunately, in 15 minutes, the sun's moved quite a lot to a robot. So if it takes another image 15 minutes later and tries to compare the images, there's a big difference because those shadows have changed so much, and it really threw the robot. It was a real big problem for the robot. It was using stereo vision, so it was having separate left and right cameras and comparing the differences between the 2 images to determine depth. Okay, so looking at the behaviour-based robotics, Alan was developed by Rodney Brooks, and Rodney Brooks developed a subsumption architecture. Now, subsumption architecture really mimics the way that we work. It divides the processing of the robot into many, many different layers, and just 3 layers have been put here as an example. And you can just liken it to you're walking around a busy town on a Friday night when you want to go to the pub and get a kebab and go to a nightclub, for example. Okay, you've got different behaviours going on. Now, the most basic behaviour that you've got to do if you're walking around town is avoid contact with people. Okay, you don't want to go around bumping into people. So that, again, is the most important behaviour for a robot. And then, okay, so you're doing that and that's fine. So what's the next behaviour that can work once this is working? Okay, so if that's all working fine, avoiding contact, then you can wander, you can find your location, you can find where you want to go. So you're wandering around, you're exploring the town, and then the next higher behaviour might be, well, explore if you see something useful, or if you like the look of a certain establishment, go into the establishment. So it's different behaviours that are happening all of the time. But again, the most important behaviour is always avoid contact with obstacles. So that's a subsumption. So you might be exploring to see something useful, but then someone steps in your way. So this becomes the most important behaviour, avoid that contact again. So it always comes down to the most important. If you don't see, if the establishment doesn't look too interesting to you, then go back down to wandering. And wander as long as you're not bumping into people. So that's subsumption. So each behaviour can subsume another behaviour. So really that's the 2 schools of thought. So it's the complex control, the AI control. The robot will build up an internal world model of the area. So it'll look around at the desks and the tables and think, oh yes, there's something here, there's something there. Build it up inside. Maps the environment. And it has a centralised control and planning system. So it senses, it thinks, and then it acts. We call this horizontal decomposition because it works in a very linear fashion. So you sense, you extract the features, you combine those features into the model. So how what have I sensed relates to my internal knowledge, my internal map of the world? Plan the task, what is it going to do next? What shall I do next? Let's execute the task, control the motors and the actuators. So it's a very linear form. So the alternative to that, as I mentioned with the Braitenberg Vehicles and the Tortoise, is purely behaviour based. So there's no mapping or memory, doesn't remember where it's been, there's no centralised control. What you can do is have a bumper connected directly to a left motor, for example, or have a light connected to the speed of the drive motor. So there's no centralised control. Sensors are directly working on actuators, a bit like a knee-jerk reaction. Does mean that the reaction is very quick. Just like a knee-jerk reaction, it works instantaneously. If it hits something, it moves away. Using biology as a successful model, reacting to the real world, just senses and acts, doesn't plan. And there are ways using subsumption architecture to cope with conflicting sensor inputs. So, going back to Gray-Walter's Tortoise, the bumper would subsume the light following behaviour. So we call this vertical decomposition. So we have the sensors on the left, and there's all of these things which are going on, avoiding collisions, finding the light, following the light. And yes, you can tack on more intelligent behaviours, which would kind of subsume these behaviours, and these would be going on at the same time. So while it's doing all of these, it might build a map as well, but it's not important that it builds a map. This can be like an add-on. And then you've got the actuators. Each of these behaviours can affect the actuators. So we call it a vertical decomposition or a reactive robot. So let's have a look at some reactive robots. So we have the iRobot Roomba, and I've had one of these for years actually, and absolutely fantastic. It's broken at the moment, but it worked for about 5, 6, 7 years, way past its lifetime. Obviously, typical engineer, I've still got it. I'm going to fix it up one day, very soon. But I have replaced a lot of the parts on it, but it did an absolutely sterling job. Only quite small. Has a small bag in. Yes, you have to manually empty the bag. You put it into a room, you press the clean button, and you leave it for 40 minutes. And it's not intelligent, it moves around quite randomly, really, and it takes 4 times longer than a person would, because a person is planning where they're going. But at least it's not the person doing it, so you just leave it in the room and you forget about it. You can put a timer on it so it can start vacuum at certain times. We've got some examples of robotic lawnmowers here, and these work in very much the same way, so they don't really plan what they're doing. The only difference between the robot lawnmowers and the vacuum cleaners is these can be a bit more dangerous if they run amok, if they leave the lawn and go down the street. So when you get the robot lawnmowers, you have to get some cables that you can put in yourself, and you put them around the edge of the lawn. And those cables are sensed by an inductive sensor in the lawnmower, and it won't go beyond that cable. So it's a safety feature that has to be there. So here's a long exposure shot of Roomba in someone's room. So what's happened is they've taken a Roomba, they put a little light bulb on top of it, and they've left a camera, and they've taken a long exposure shot, probably over about half an hour, and you can see the path that the robot's taken. And the robot starts here, and it always starts off in a spiral, and it moves off in a spiral until it hits something, and then it moves around a bit like a bouncing ball, really. Now, the company iRobot won't release the algorithm. They won't tell anybody why the robot is so good at covering the room. And I've watched this robot, and it is quite fascinating, really. People wonder why it starts off with a spiral, and of course iRobot won't tell you, but some people say, well, maybe it's doing a spiral and it's using its sensors to get an idea of the size of the room, but nobody really knows. It has got those sensors in, and those sensors are used when it's approaching a wall, it slows down. It's also got bumper sensors as well. So it slows down before it hits an object, and then it just hits it quite gently. Sometimes the robot will be going along in a straight line and then just turn at a random angle for no apparent reason. So it's got some sort of timer in there and decides to turn. What I would say is that when iRobot have developed this robot, they have most likely created a simulation of the robot and tried different algorithms and say, well, after 15 seconds, if I don't bump into something, turn a random amount or turn 45 degrees. They could try different ideas. They could run all of these simulations extremely quickly, and they could even have a program that says what's the best coverage. Of course, everyone's room is different, but there must be ways that if you always do a 45 degree, if you hit a wall, you're probably never going to fully cover the room. So there must be some random element in there. But it's quite nice. You can see that it covers things quite nicely. Some areas it covers more than others. But, pretty much randomly, everything's been covered. So, Braitenberg Vehicles, as I mentioned, you had the Grey Walter Tortoises, and then Valentino Braitenberg, another psychologist, wrote a book called Experiments in Synthetic Psychology, the title being Vehicles. This is a beautiful book. I've got a copy myself. I just bought my own personal copy. It's only a thin book. And what Braitenberg wanted to create was animals. He didn't create real animals. He made them made thought experiment animals. He wasn't interested in robotics, but he was interested in understanding how animals and humans can work. So here's a very simple vehicle. He divided these vehicles into vehicle 1, vehicle 2, vehicle 3, vehicle 4, all with increasing complexity. Vehicle 1 is connected to has a sensor, which is this symbol here, this curved symbol, and a motor on the back. And what you could say is that vehicle could be something that could go in the ocean. Very simple vehicle. And if it was a temperature sensor, for example, the more temperature, the higher the temperature that senses, the faster the motor, when that motor might be connected to a propeller. So you can see the direct connection between sensor and actuator just means that the more it senses of something, the faster the motor moves. And you could say, well, has it got a behaviour? So it seems to be quite sluggish in cold water, but it moves quickly through warm. So is it alive? Does it seem more lively when it's in warm water? You can put two of these vehicles together. So vehicle number 2 is built on 2 of vehicle number 1's. So for example, let's have a look at a mobile robot. So you've got a sensor connected to a left wheel and a sensor on the right connected to a right wheel. And there's 2 pluses here because that just means that the sensor will positively affect the motor. And if you have a light source here, and these are light sensors, then robot A, vehicle A, will move and shy away from the light because the sensor on the right senses the light more than the sensor on the left, so this wheel will move faster. But if you cross these round, then your left sensor is affecting your right motor, and you've got something that likes the light. Now, in a robot system, you could have these either crossed or uncrossed depending on its current state. For example, it might be a solar-powered robot that needs to charge, so it might be in this state. And then, if it's fully charged, it could go into this state because it needs to get away from the light because it knows that other predators are around that area as well. And Braitenberg said this was fear. It fears the light, vehicle A, and aggression because it goes towards the light, and if it's just a bulb, it will go and stamp it out. It will drive over that bulb and keep going until the light's no more, and then wander off somewhere else to kick something else in. So again, you've got the complex behaviour due to complex environments. Exactly the same as Grey Walter. If you put lots of these vehicles together, and each has a light source, and some are fearful and some are aggressive, how do they behave? How do they interact with each other? It's quite a nice little thought experiment. Now, if you do a search for Braitenberg, probably Braitenberg would be the best thing. You can find simulators online where you can create your own vehicles and put vehicles into an environment and see how they behave with each other. So it's a nice little psychological tool. So I'm going to talk a little bit about basic algorithms. So what's the algorithm to follow a line using a single sensor? We can make a robot almost become lifelike and move along a black line just using a single sensor. And the simplest way of doing that would be to make a vehicle. vehicle 1 really. If we have vehicle 1 connected between the sensor and the right motor, and let's take the left motor out of the equation. I always find with any kind of engineering, keep it as simple as possible. So if we have the left wheel at a medium speed, so it's always running at half speed constantly as soon as you put the battery on, and the right wheel moves at a speed which is proportional to the light that the sensor receives. If it receives a very bright area, then the right wheel moves faster than the left wheel, and if it's on the black, then the right wheel moves slower than the left wheel. And you can probably see how this vehicle will start to follow the line. It doesn't really follow the line, but it follows the edge of the line. So it's on the white, so the right motor will guide it towards the black of the line. And when it's on the black of the line, that slows down, so the left motor is going faster, so it moves away from the line. So we've got a very simple line-following vehicle, line-following robot. It almost seems to sniff the line. If you make one of these, it looks quite lifelike, because it looks like a dog on a trail. It goes off the scent, on the scent, off and on. So we've made something fairly intelligent just from that simple algorithm. We could make it a little bit better. So that would be a nice basic line following algorithm, but let's say we wanted to have an automatic car to drive along the motorway. And also it makes you think about how do we drive along the motorway? If it's late at night, there's no other cars, and we can be on the left-hand side, and you're tired, so you just want to keep driving nice and simple. You keep your speed, or you can put the cruise control on, and all you need to do is just keep hold of the wheel, right? And we're constantly adjusting that steering wheel. We can't tie a bungee cord around it and read the paper. We have to do some constant adjustments. I'm sure some people do, but I don't know. And what we're doing is if we simplify it, we're looking at the line on the left-hand side of the hard shoulder, and we're keeping a distance from that line. And we're doing that with our steering. So we're looking at the distance of the line, and we say, well, I don't want to be closer than a metre, but I don't want to be more than 2 metres away from it. So we're proportionally moving. And if that line on the left starts to drift away very quickly, we know that we're drifting too far to the right, so we would maybe turn a bit faster towards the left-hand side. You can do something very simple and very similar with the robot. Again, we keep the left wheel a constant speed, and because this motor is proportional to the amount of light that the sensor sees, if it's half on the line and half off the line, if it's tuned nicely, then these two motors should run at the same speed, so it will be on the line quite nicely. If it drifts away from the line slightly into the white, then it slightly speeds up the right motor, which makes it drift back towards the black. If it drifts too far into the black, it slows down proportionally, this motor, so it drifts back, so it's constantly hunting, which is exactly what we do. If you had to apply that to an Ackermann-steered robot, in other words a robot car, then you could say that the steering wheel position depends on the amount of light received. If it's half on the black and half off, the steering wheel's in the middle. If it's going towards the white, then it moves more to the left. The more on the white it is, the more it moves the steering wheel to the left. So you've got that feedback, that proportional control. Vice versa, if it's on the black, it steers more to the right. So you're hunting. Anyway, I love the title of this paper. Rodney Brooks, with his behaviour-based robotics, created a paper called Fast, Cheap and Out of Control. So what Rodney Brooks wanted to do was to land lots of small robots on the moon and leave them all out of control, basically, which is why NASA rejected it. At the time, NASA was spending a lot of money developing a single robot with lots of technology, lots of artificial intelligence, to land on the moon, but it would be predictable. We would know how it would behave if it saw certain objects and certain sensors. Rodney Brooks, on the other hand, had an idea that let's create many robots, a bit like Gray Walter's tortoises, 100 robots or so. They'd be very cheap, they've only got very simple sensors on, they have reaction, but they're all connected with each other. They're fast because they'd be fast to develop, because it's simple, so let's not put too much artificial intelligence in it. Let's just put them all together and have communication. They're out of control because, yeah, you can't really say what they're going to do next. If they see an object, they move out of the way of it. That's it. But those robots would be covering a bigger area than a single robot. And if you lost one or two down a crater or a Martian picked one up and took it home or something, it doesn't really matter because all of the others are still in communication. So you've got a much wider area of data acquisition than just losing one simple robot. So that's the whole idea behind that. Yes, it was thrown out because aerospace don't like anything that you can't predict how it's going to happen exactly. So the out of control was a great title for a paper, but do favours for Rodney Brooks. Okay, just before the break, I'm going to show you how a maze solver algorithm works. It's very simple, it'll only take a few minutes. But it does introduce you to the idea of algorithms. So you've seen one algorithm, which was a line-following algorithm. So let me show you how robots can plan their way around, how they can solve a maze. You can use this to solve mazes that you find on the back of cereal packets even as well. Okay, let's make life really simple. And let's imagine we have a room, it could be this room, and let's divide the room into metre squares. And let's say that the room is only 4 metres by 4 metres. So each one of these blocks represents 1 metre square. And let's say that the exit to the room is this block here, connected to this block, where the end is. And the robot is at the start position. Now it's got to get from start to end whilst avoiding these black blocks. So that anything black says there's an obstacle in the way, don't go there. So obviously it can't go along the top and then down to the end, or down to the bottom. We can immediately see the best route. Or there might be a couple of routes really that we could follow, it doesn't really matter. But how would a robot do that? And this is actually applied to how on earth does your sat-nav work out the best route to go? What happens there? And what it does is it cheats. So your sat-nav cheats, the algorithm cheats, just like anybody who's good at cheating at mazes, the best way to do it is always start at the end and work back to the start. So you know how to get there and you say, okay, what's the best way? You know the result. How do you what's the best way to get to that result? So here's a simple algorithm. And what we're going to do is the robot is going to have an internal map of its environment now. So I said those are 1 metre squares with objects in the way. The robot has built up in its memory bank a row of, well, a matrix of what's 4 by 4, so that would be 16 little squares. And each of those squares is just a memory element, so it contains a number. And it can contain the number between 0 and 255, because it's just a little 8-bit memory cell. So we'll say 255 is going to represent an obstacle. It's just a high number. And a 0 is everything that I've unexplored, so I've not been there yet. So everything I don't know is a 0, every obstacle is a 255, and we're going to place the number 1 at the end, at the goal position. So the computer's representation overlaid onto the real representation looks like this. So high number for obstacles, doesn't want to go there. 0's unexplored, not been there, and a 1 at the goal position. In the computer's memory is going to run through a little program, and the program is going to be this. So start at an array value of 1, or it could be, I should say, memory value of 1. Okay. Add 1 to every adjacent square that's a 0. And I'm going to use 4-point connectivity. That means I'm just going to look up, down, left and right, north, south, east, west. I'm not going to go diagonal. So every square that's adjacent to that number, add a 1 to it. So we start at 1 and we're going to put 2 there. So it will look like this. So we start at the 1 and we're going to, every adjacent square, so up, down, left, right. We can't go down and we can't go right. We're going to put the next higher number. So we have a 2. And then we repeat the algorithm. So start from the memory value of 2, add a 1 to every adjacent square. That is a 0 that's unexplored. So we have a 3. Next to the 2s we have a 3. And you can see there's a bit of a routine. So we're going to continue. We're going to look for the 3s now and add the next higher number. So we'll take the 3s And every value that's got a 0 in, we're going to put the next higher number, so there'll be a 4. We can't do these ones because they're filled with numbers already. So we have our 4. Let's repeat that and put 5. So we'll have a 5 and a 5. Let's repeat it again. 6. Got our 6s. See that we've got a 6 over there as well. Repeat it. 7. Repeat it until every memory value has a number in. So to find the path, you start from the goal. You turn left, right, or continue straight on. So that's all the robot can do. It can go into the next cell. But it always goes to a lower numbered cell. Or very rarely, you might have the same numbered cell if no lower one exists, but it doesn't happen very often. But never a higher numbered cell. And this is a bit like a ball rolling down a hill. It always goes to a lower number, the lower number being the height, so it always follows its way down, flows. The robot knows when it's reached its goal position when the memory value is. So we can start from here. Which way do we go? We go to 6. Okay, which way do I go now? I go to 5. Which way do I go? Go to 4. Go to 3. Now here I can have a choice. I can either go to 2 and to 1 across the top, or down and there. It just depends on the search algorithm which comes first, really. It doesn't really matter. We still get the result. So this is applied to any kind of road following algorithm. If you want to get your route to London, it's got the values of all of the roads coming out of London, and it just puts the next value coming out of those roads at every junction. So the kind of numbers we're dealing with is goes up to thousands, millions probably, because of all the junctions. But there's probably some artificial intelligence that says, well, if it's going off in the wrong direction, don't bother doing that search. Okay, I was kind of searching the correct direction. So it will choose the junction of the next lowest number, so it will tell you when to turn left and right. Of course, there's more you can put in there. Avoiding toll roads, for example. Avoiding lakes. We've got a. You can build on this, obviously. If you want to look this up, there are 2 routines to it, really. One is called the grass fire algorithm, because if you start a fire here, it spreads. Okay. There is a more improved algorithm, which includes things like toll roads, if you like, or wheel slippage, or areas that you don't really want to go, and that's called the A-star algorithm, the A-star search algorithm. But what's very nice about this algorithm is the robot can start anywhere and always get to its goal position. So if it started here, it tells you the route down. If you started here, it shows you the route there. And what I'll do is I've written a simple program in Excel that solves this. So you can have a play with this on a 10 by 10 grid. So I'll send that off to Sven, and you can have a bit of a play. You can try and confuse it by putting obstacles in there. Put your start position, put your goal position, and then see how it gets solved. Okay, so I think we'll have a break there. So shall we have a break for 10? I've got an algorithm that we've tested out to cover the wall, the floor. Well, how do they do that? How can you say where a robot will be? So I'm going to introduce you to some very basic kinematics. It's very basic robot modelling that you can apply. Just a straightforward idea, and you can make it, apply it to vehicles or all sorts. So robot kinematics says, well, localization, how far has a robot gone? So let's have a look at a vacuum cleaning robot, and it's got wheels on the left and wheels on the right, and it moves. So you drive both of these wheels. How far has it gone? How far is it translated? If you run a right wheel faster than the left wheel, it's going to rotate as well. So the simple kinematic equation says that you've got distance and angle. So the robot has only got 2 degrees of freedom. It's got its distance and its angle that it's rotated. And if we just make things nice and easy and say, okay, we know the circumference of these wheels, and we've got encoders on these wheels as well, so we know how far the wheel is rotated. Okay, so remember encoders from last time? Basically a disc with lots of holes in it. So you know the distance that the left side has moved, and the distance at the right side has moved. So the simple kinematic equation for the total distance, and that would be from the centre of the robot to the centre of the new position of the robot, taken over a sample time, would simply be the average of the two. So the left plus the right divided by 2. So I said it's got 2 degrees of freedom, so it rotates an angle as well. And what is that angle? Well, the value is the right wheel, subtract the left, divided by W. And W is the width, or the distance between the 2 wheels. So have a think about which direction is a positive angle from that equation. And then further think about what units is this in? Anyone hazard a guess?
Radians.
Yeah. And positive?
Anti-clockwise.
Yes, positive would be anti-clockwise because the right is on that side, yeah, on the right-hand side. Yeah, so the value radians and positive angle is moving to the left-hand side, anti-clockwise. So you can add those values together, and every sample time you can read the encoders and know where your robot would be. You can simulate your robot, which is what I've done. I'll try and show you some examples a bit later on of a simulated robot. You wrote the program and you're seeing how it can behave, where it would be. You're simulating where objects can be and how it behaves to that. Now, this, the next area I just wanted to mention is state programming. So remember I spoke about subsumption and the different states that you can be in. You're avoiding obstacles or you're going to a location. Well, you can do exactly the same with robotics as well. So just here's an example of some code that might realise how robots can move to through different states. Let's say, for example, this is taken from a assignment that some students have to do. They have to program a robot to start at the A location, move to E, go along to B, C, D, then go to E, and then make a decision to turn left to go back to the home position. And when they're back in the home position, the robot needs to turn around 180 degrees. And one way of looking at this would be to use state programming. Now, the first state that the robot's in is waiting for the start button to be pressed. It shouldn't move until you press the start button. So that's state number 1. And then state number 2 would be, okay, you've pressed the start button, now I'm moving to point E. And it could use a line following procedure to go to point E. When it determines that it's at point E, and I call it E1 actually, because it's this point of E, it's coming from the direction of A. The next state could be, okay, I've moved to point E2. So E2 could be, follow this line around until I'm at E again. And then the next state might be move to A2. So it knows that the sensors can recognise a T-junction and it has to move left to follow the line to A. And I call it A2 because it's approaching A. When it's at the A position, it needs to sense that somehow and then moves to the next state, which could be turning 180 degrees. So the state can be realised with a programming language. So I don't know if you've ever covered a basic programming language, but you can have a variable which could represent the state, and then the code just says, well, if I'm in state 1, then go sub state 1, which would be waiting for a button to be pressed. If my state is 2, then go to this state 2, which is a line following procedure. Now, at the end of each state, there has to be a way of either keeping the same state that it's in, or increasing the state. Now, in this example, B0 represents your state value. If the button has been pressed, then B0 equals 2, which means go to state value number 2. The code returns and it says, okay, I'm going to go to state number 2 and then do the line following procedure. And it might be if a sensor sees the line on the right hand side, then it makes the state into state number 3. It says, okay, I'll go into state number 3, and that could be doing something else, or it determines when it's at this T-junction from this angle. So it's about states. So that's how robots work with different areas. For example, a state of the vacuum cleaner robot might be, my battery is low, I need to find the charging station. So that state subsumes the state of cleaning the floor and following that pattern. So it's just about robots move from different ideas. Your state on a Friday might be go to the first pub. After several pints, your state might be find a kebab house. Your state might be find a nightclub or find the way home. We move through different states in robotics, and they have different importances depending on our current senses. Hunger state, or beer requesting sensors. I'm sure there's beer requesting sensors somewhere. Okay, so I've talked about mobile robots, which really applies to agriculture. But I will just talk a little bit about industrial robot arms. I cut my teeth on robotics with robot arms, so I'm quite happy using these things. Interestingly enough, a lot of robot arms are made by motorbike manufacturers in Japan. So you have robots like Kawasaki, quite popular. Toshiba make robots. Epson make very fast robots as well. ABB, Kuka, Fanuc. So some German, a lot of Japanese. So just here's some examples of how robot arms move. I don't know if these little things go, but I've just taken this from How Stuff Works. If you do a search for robotics on this website, it can show you that basically robots are divided into a robot base, which rotates, the shoulder, exactly the same as our shoulder, elbow and forearm, and then the end effector. The end effector could be a gripper, it could be a hook, it could be a sucker. It doesn't have to be fingers. The forearm usually does this dexterous bit, so it's usually got the pitch, the roll, and the yaw. And then you've got your end effector. So you've got your different motions. And usually there are 6 motors in industrial robot arms. We call it 6 degrees of freedom. So the ones missing from this are the pitch and the roll and the yaw, some have, so that's 5, 6. Yeah, the forearm is actually represents roll, pitch, yaw. So 6 degrees of freedom is quite average. Here's an example of a robot with a welding head on. So no need for a gripper, all it does is welding, so it's got that permanently attached to it. So you've got your base motor here, your shoulder motor, your elbow motor, and then it deviates a little bit from a human, because after the elbow motor you've got a motor here which rotates the whole forearm, like that. And you've also got a pitch motor, so combined with this motor after the elbow and the pitch motor, you've got this degree of freedom where you can rotate a tool. Now, what they have at the end here as well is a rotation. So you've got your forearm rotation, your pitch, and then you've got a rotation. We don't really have the same thing, but if I rotate my fingers, it's a bit like turning a screwdriver in a certain area. So they've got that degree of freedom as well. So what kind of things do they do? Well, pretty much anything. I program robots to do pick and placing, palletizing, materials handling. I've not done any of these, paint spraying. I've not done assembly, but drilling and grinding. These are actually quite interesting tasks, because if you think about drilling, robots originally were position robots, so you would send it to a position and it would stay there. Right, I've gone to that position, I've moved something there, fantastic. But with items like drilling, it's not a position problem. Yes, it moves the drill to a position, but then it becomes a force control problem, because you're drilling a hole. What do? You move the drill to the right position, but then you apply a force and let the drill take control, really, and you can feel, are you pushing too hard, are you pushing too soft, and your position becomes secondary. It's the force which is the most important. So robots now can apply forces and go into force control mode whilst monitoring the position. Same with grinding. As that grinding wheel gets smaller, you want to be able to compensate for that. So it's not good going to a point. You want to apply a certain amount of force, but not too much force. Assembly. A common problem with robotics, or a common assembly project, is called peg in hole. So you're assembling a peg into a hole. But how do you put a peg into a hole? And when they were starting to First of all, they put on compliant wrists. So between the gripper and the robot, you had some kind of rubber compliancy. So that was the initial idea. But now manufacturing robots can go into this force mode where they will push something down, but with force control, and allow the peg to move the robot. So they allow for that compliance. And in fact now, robotics are starting to work amongst humans, because these kind of robots have to be separated from people. They have no sensors, and they will just keep moving and take someone's head off if you get in the way. But with a lot of manufacturing, they want robots to work around people and amongst people, because they take up a lot of space if you have to separate them. But if you've got force control on, you can have them working around people, and if you lower the power of the motors, so if a person does bump into it, it's not going to hurt too much. It's got sensors on anyway. So force control is the big area of robots nowadays. So I'll talk about some basic joints of a robot. You have a revolute joint, so this is your most common type of joint. You can have a prismatic joint as well. So you might remember the plotters that we used to have. So they were prismatic motors, so linear motors. You also get Cartesian robots that will work a bit like a plotter. You can imagine a shipping container place that moves shipping containers. That can be a Cartesian robot. Depends who's operating it, but it's a prismatic joint. You can get spherical joints on robots as well for the wrist end effector, so it can move in 3 degrees of freedom. 3 degrees of freedom would be up, down, to the right, and then a rotation, so actually 3 degrees of freedom. And basically consist of those. So have a look at your basic Revolute type of robot. So this is the same as the Kawasaki robot that I showed at the start. This is generally what people think of when they think of. So 6 revolute joints. You also have a SCARA type of robot. I might have a picture. Ah, there we go, that's a bit better. So a SCARA robot was made because of this peg in the hole problem. So the joints of the robot, it basically moves in a horizontal fashion. What's very clever about this robot is if it's putting a peg into a hole, if you release the power of the elbow and the shoulder motors, it's still going to keep that position, but as the shaft moves to put the peg into the hole, the peg will allow these joints to comply, the elbow and the shoulder joints to comply. So this is why this is used in assembly. Actually, SCARA stands for Selectively Compliant Arm for Robotic Assembly. So it's selectively compliant because if it's putting a peg into a hole, it can turn these motors off, so it becomes compliant, selectively compliant.
When you say a peg and hole, does that mean a bolt?
It could be a bolt, or it could be an axle that's going into an axle housing. I remember building an engine once, an old VW engine, and there were certain shafts that I had to put into that engine, and it was I can't remember which part of the engine it was now, but it took me ages because it was the tolerances were so tight that rattling it, I couldn't even do it. I had to try it and try it again. So it's any kind of assembly task, really. Yeah, it could be a bolt, but a bolt, yeah, you tend to turn and it tends to comply its way in as well.
Does it learn its compliance, or do you program it?
You program it in. So initially, you can turn these two motors off, and that becomes a natural compliance. You can also lower the power to these motors. So you can say, well, I want these motors to be on, but with 10% power. So what it will do is it will hold its position, but if you go up to the arm and push it, it's like a spring, it will move out of the way. And you can change the compliance. You can make it a tight spring, or you can make it a soft spring, but it'll always come back again. So that's what they tend to do. Initially, they just turn the power off, but now they have amount of power control on the robots. So it's your selective compliance. And these are the type of robots you get in circuit board manufacture as well when they're moving, because these robots are very fast. They're a lot faster than the Revolute arms, and the reason why is with a Revolute robot arm, each joint has to support the next joint along. So the shoulder joint has to be really, really powerful motor. But with these, the shoulder joint isn't overcoming gravity, it's only overcoming inertia because of the way it's built. So you can get cheaper, smaller motors and faster as well because it's not having to compensate for gravity, both with the shoulder and the elbow motors. And then you get the Cartesian or gantry type robots, or plotter if you like. Now the good thing about these is they're very good at moving in straight lines. Funny enough, the SCARA and the Revolute robots can't move in straight lines because the joints, there's nothing straight in there. So if you ask a robot to go from one position to another and plotted the line that it's taken, it would not be in a straight line. Only a gantry or Cartesian robot will move in a straight line because each of the joints of a robot, of a Revolute robot, will just move as fast as they can to get to a point, and they tend to jump. There are ways of making it follow a straight line, but you have to put lots of intermediate points. So if you say point-to-point motion, my Revolute robot is going from one position and it needs to reach to another position, the line that it will follow will probably be a loop, which is no good if you're working on a table and it's got to move something from one place to another, but make sure it's going in a straight line because it might lift it like that, or it might try and push it through the table. So the only way to do it is to calculate what is a straight line, if you wanted to do a straight line, and say, well, I want you to go from point A to point B, but go along this line, and I'll keep you going along this line by having lots of points along the way. So really, there's lots of little leaps. But those leaps are so small that it looks like a straight line. This is called continuous path motion, going in a straight line, and this is called point-to-point motion if it just goes from point A to point B. Point-to-point motion is a lot faster. Continuous path is a lot slower, but a lot more accurate. So when you program in industrial robot arms and you say, right, move to the coffee cup, you can either say point-to-point or continuous path to that coffee cup. But if the path isn't important, then you say point-to-point because it will go there very, very quickly.
Possibly a slightly odd question. So if you've got so something like a laser profile cutter, this would be a Cartesian robot. So, but if you're cutting holes and cutting shapes, you want a very high resolution to do so, to do that. Would that take more? Presumably that take more processing than a robot arm.
If you're trying to cut
cost-wise, would the cost comparison between that? If it's sort of doing a material handling role and then it's doing a.
I mean, if you were just cutting shapes, then it would be best to use a Cartesian robot because it's easier to program. Each joint isn't responsible for the next joint, so you've got accuracy in the X and accuracy in the Y. They're very cheap. They're around about 10 grand. You buy the individual X and the Y components separately, so you can make it as large or as small as you like. But then if it had to handle something, Cartesian robots can't do that. They can only do that. So they're great at working in shipping container areas, but if it had to then handle something, then you'd have to either have two robots or, you could do it with a Revolute robot, but it would be a not very accurate way of doing it. Their accuracy isn't as good as a Cartesian. So just talking a bit about accuracy, you can see why a Revolute robot is not very accurate really, because the accuracy of the endpoint relies on the accuracy of not only the base rotation but also the shoulder. And the longer these joints are of the elbow and the shoulder, the more that can move. So accuracy is a big problem. And also payload. So if you're carrying something here and the arm's outstretched, the payload is going to be a lot lower than if the arm is here as well. So it really does change things. When you buy a robot arm, it tells you a maximum payload, and that's at the worst possible scenario case of outstretched. The ones I've worked with are about 5 kilo payload, 10 kilo payload. You can get 100 kilo payloads as well. And you get the KUKA robot arm, which actually has 2 seats attached to it, and I've seen these at shows, and you can get on it and have a ride. And it's a big robot, and it will throw you around. And you can generate your own roller coaster ride, because you can say how you want the robot to move, so it's quite cool, really. So, just talking about robot kinematics, so again, as I spoke about mobile robot kinematics, where am I from knowing those sensors? We've got encoders in the base, shoulder, elbow, wrist. Knowing those angles, you can calculate the endpoint. But you can see that you're talking 3 dimensions, and it can get fairly complicated as well. But it's all robot modelling and testing. Okay, so I'm going to tell you a bit about the robots that we have here at Harper Adams. So you see one of the robots that was built by some master's students about a year ago now. This one is in the AEIC, so you can go and see that. It's got the bumper that I was talking about with the sensors. You can see the size of the bumper. It's got a LiDAR on it. No seat, no steering wheel. The idea is it's to be autonomous. We have a larger robot, which is an orchard tractor robot, which gets taken out to Sweden. So we're testing this out, not Sweden, Switzerland. Switzerland is going again this year to autonomously work through orchards using its LiDAR scanner and using GPS and take readings of the environment, of the canopy, using laser rangers to see how much the canopy cover is. We also build some of our own UAVs. We've got lots of UAVs here. We're looking at making these smaller and smaller using rapid prototyping materials that we we're not the only ones to make robotic tractors. There is a Future Farm Objective, which is a European research platform, and it's all about precision farming, autonomously controlled tractors, and some nice different ones here. Quite like this one, which has got independently controlled steering wheels, so it can move crab-like if it needs to. So you might see some of these pictures. These were just created by Massey Ferguson for us, which just show the concept. Our robots aren't really going to look like this, but it just shows you that there's a future concepts of things. So really we're turning robotics we're turning farming on its head by using robotics, because the robots have got GPS receivers and sensors, so we can focus on the plant needs. And we're developing a farm information system. We still want to have large manned tractors for large harvesting logistics, but what we're really looking at is having smaller tractors, small vehicles, and I'm talking pretty small, that won't compact the ground. They're all in communication with each other, and they're behaviour-based and planning-based as well. And we're looking at 4 stages: crop establishment, crop scouting, care, and selective harvesting. So these are some of the requirements that we have just from a bit of a brainstorm. What do we need with our robots? The main one is lightweight. We want it lightweight because we want it to be able to work in soft soil. We want the robots to be able to work when it's been raining and not compact the soil too much. Small and autonomous, computational and energetic autonomy, so be able to charge itself up, be able to plan its paths. Weather independent, so it can work when it's raining. Redundant system architecture is something you find with robotics. It means if something breaks, the robot can plod on. So the robot on Mars that lost, one of its the motors to the wheel jammed, it can use the other motors to compensate for that. So it's a redundant architecture, which leads on to graceful degradation. If a few sensors stop working, can the other sensors compensate for that? So we don't want the robot to stop and have to have someone fix it every time one little thing goes wrong with it. Communication, we want to be able to understand what it's doing. Self-awareness, so it knows if it should stop, if there's objects in the way. Be able to work at night, for example. For example, a robot could just wait. So if it's spraying, if the wind goes up, can it wait until the wind dies down and then continue? So what we've developed is a route planning software, and this is an image of Harper Adams. Actually, the engineering building's here now. This is taken from Google Earth. Now this is our software, so it integrates with Google Earth, and what you can do is plan the outline of the field. It creates the GPS coordinates from that plan, and then you say what width of implement does the robot need to use, or the vehicle, and the software will plan the most optimal route to cover that field. whilst minimising the amount of headland turns. So sometimes the results are not what you would imagine. Sometimes it goes diagonal. It just depends on the outlay of the field. He doesn't care about the longest part of the field or north, south, east, west. He's got an algorithm that looks at the most efficient coverage. So let's just play this again. So we have a real simulator for vehicles. Which saves us having to go out into the field every time, and if something goes wrong. So you can see the robot coming in here. All of these points are the waypoints. So the route planning software creates waypoints that the vehicle should aim for. So it aims for the next waypoint, turns around, does a bit of overshoot because it can't follow it, as accurately as it needs to sometimes. You can also see the coverage. Sometimes you'll see a lighter green coming out, and that's the coverage that the robot is making. It's coming to a headland turn now. See the coverage, just updates it every now and then. This is what the farm manager would see, the position of the robot. It's moving around the headland. This would be the real robot, or the simulator that we're using. It doesn't matter whether we're simulating it or it's a real thing, it should be all the same.
Oh, fine.
And with our software we can also look at different viewpoints. So this is the simulated one. Let's get a bird's eye view and see how is it covering, and is there any overlap. It stops doing its work as it turns at the headland and then resumes again. You can see that there's minimal overlap at these points, and there's only a small amount that it's missed. So the robotic seeder that we've developed, so very light, low draft force, no agronomic compaction, so it can put the seed in the ground in any weather, whether it's rain or shine. Cultivate for each individual seed position, so it can store the value of each, the position of each seed. It could even change the seeding depth depending on the moisture and germination rates. So this is the robot in action, built by our master's students. This was taken a year ago just outside. Now this field was at field capacity, which means it was almost waterlogged. You put in a litre of water, you'd get a litre out, so you can't take any more. It's not autonomous at the moment. This is being radio controlled just to show the dexterity of the robot. So it's front and rear wheel steered by these students here. Now by walking onto that field, here you've got a flooded footprint, but next to it you've got the tyre track, which shows that the pressure of that vehicle is not as great as a human's footprint. So if we look at weeding, I'm quite interested in organic weeding, which can be made simpler by synchronized planting. So we can have many robots, very precise timed location of putting the seeds into the ground, which makes things like weeding simpler because you can weed in between. For example, you can weed in that direction, taking out anything that's red, and weed in the vertical direction. We're also looking at laser weeding, so can we use a camera to recognise rows of crops, and can we also use a camera to recognise weeds and the growing point of the weeds, the meristem of the weed. And if we can recognise that growing point, can we do something about it by using the least amount of energy? If we recognise a weed, we could use a small amount of pesticide or herbicide. Rather than spraying the whole area, can we just recognise the weed locations and just spray those bits that we need to? So can we go completely organic and use lasers just to focus on the plant? Now what we're doing is, with our lasers, we're not trying to blast the plant out of the soil. That would be fun, but it would take a lot of power. What we're doing is we're just trying to heat up the cell walls of the meristem to rupture the meristem, just that growing point, just a few of the cells, using as least power as possible and as quickly as possible to just disrupt those weeds. So they won't die straight away, but they will die after about a week. They won't continue to grow.
So the idea of using the sort of flame.
Yeah, exactly, to rupture the cell walls. Yeah. And in fact, we could use it. Yeah, if we can recognise the weeds, we can use a flamethrower. We have a robot Tortoise, which is now in Greece, which was developed by master's students a few years ago. And this had several sensors on, multispectral camera for nutrient status, LiDAR, so a laser ranger, for canopy extent, so it's looking to see how much does the canopy, is it growing. This is for vineyards. And this is a modified quad bike, probably notice. Robotics is a robot which has been developed in Denmark specifically for cropping. So rather than taking an existing robot, they've completely rebuilt this robot. So it's quite efficient. It's got tank tracks on it that moves autonomously.
It's like a mini gantry.
Yeah. We have our UAV research as well, where you can have a rapid assessment of crops. One idea that's been done is to use UAVs to plant seeds, certainly in rice paddies, where they can just fly over a flooded rice field and just open up a bucket with the rice seeds in and let the wind blow the seeds around. And we can kit these out with, we have 6-rotor UAVs, so they've got quite a high payload, so they can carry all sorts of sensors here, NVDI, thermal, multispectral cameras. And talking about selective harvesting, so why harvest everything in a field? Up to 60% of harvested crop is not saleable. So only harvest that part of the crop which has grown and is ready to harvest. You could look at the quality and separate them as you're harvesting. So you can grade them for packing and sort them, grade for quality. So you're minimising the off-farm grading and sorting. So the concept here is that we have this robot system with the sensors that looks at the harvest quality. You can see that it's left some behind and it knows the location of each. So the focus is on the individual plant leads. The GPS coordinates of all of these plants has been stored. The robot can come back to those in a week or two. It can grade them, it can sort them, and in the back we can have the storage and it can separate the storage. So the back part is a trailer.